Hi everybody, welcome back to my channel on Feynman integration. Today we'll be going over the solution to my video titled Can You Solve It? Episode 6. Alright, let's get started. So just as in my example 68 and 69 video, we're going to split this up into two separate integrals, one going from 0 to 1 and one going from 1 to infinity. So that will give us our I is equal to the integral from 0 to 1 of natural log x over square root of x plus 1 cubed dx plus the integral from 1 to infinity of natural log x over square root of x plus 1 all cubed dx. All right. Now I'm not going to perform the u substitution in here. I'm just going to take x to 1 over x. So 1 over infinity is 0. 1 over 1 is 1. Natural log 1 over x. This will come up to the top as an x to the, we'll write that as x to the 1 half. This will be 1 over x, and then we will recover a negative 1 over x squared also. So we will use the negative to switch the bounds, and the x squared will be on the denominator. Now we will multiply the top and the bottom by x squared. This will become x cubed, and this will become x to the 3 halves. All right. This natural log 1 over x will become negative natural log x. So we'll use that to switch that to a negative sign, and we will distribute this x cubed inside the parentheses, giving us back our desired x plus 1 cubed. Great, so now we have two separate integrals that look very similar. In fact, I'm going to write this as x to the negative 1 half. Okay, so now we're ready to create a function of t. So our function of t is going to be equal to the integral from 0 to 1 of x to the t over x plus 1 cubed dx, and our f prime of t, which we obtain using the Leibniz rule for differentiation under the integral sign, is equal to the integral from 0 to 1 of x to the t natural log x over x plus 1 cubed dx. Excuse me one second. Okay, sorry about that. Okay, from here we can see that we can recover our original integral like this. If we evaluate our function, our f prime of t at the point negative 1 half, and then subtract f prime at 3 halves, we will get back our original integral. So I'll write that up here. So I is going to be equal to f prime evaluated at negative 1 half, that will give us this part, and then minus f prime evaluated at 3 halves. That would give us this part, which equals I. And I'll just put a box around this. All right. So, next step, we want to find a new representation for our f of t, because it doesn't do us any good as is. As in my previous two videos, we need to find a Taylor series representation for some part of this integral, and the part that's pretty obvious to choose is 1 over x plus 1 cubed. So, we know this. We know that the sum from n equals 0 to infinity of negative 1 to the n times x to the n is equal to 1 over 1 plus x on the interval negative 1 to 1. One of the bounds is included, one of them isn't. I'm not sure, it doesn't matter. So taking two derivatives with respect to x on both sides of this equation will give us this. We'll have the sum from n equals 0 to infinity of negative 1 to the n times n minus 1 times x to the n minus 2. And that will be equal to, let's see, two derivatives of this with respect to x. That would be a negative times a negative, so positive 2 over 1 plus x cubed. All right. Dividing both sides by 2, and we get 1/2 on that side. So now we're ready to sub this in for our 1 over 1 plus x cubed in our original f of t. So that's going to give us, let's see, that would give us f of t is equal to, well, let's see, we still have the integral from 0 to 1, and we still have our x to the t, but now instead of the 1 over x plus 1 cubed, we have the sum going from 0 to infinity of negative, and we can't forget this 1/2, which I'll just bring right outside the integral. So we have negative 1 to the n times n minus 1 times x to the n minus 2, and then all of that dx. All right, let's make sure I copied that down right. We still have the integral going from 0 to 1. We have the x to the t, and we have the 1 over x plus 1 cubed is equal to 1/2 the sum from n equals 0 to infinity, negative 1 to the n times n minus 1 times x to the n minus 2 dx. So now we're going to perform some manipulation on this. We'll bring this x to the t inside by just adding a t here. And then we'll switch the sum and the integral signs. So we'll now have, this will be the integral from 0 to 1, and this will be the sum from 0 to infinity. Oops. N equals 0 to infinity. We'll bring out the negative 1 to the n. We'll bring out the n. And we'll bring out the n minus 1. And we'll move this integral over a little bit. So now we have the integral from 0 to 1 of x to the n plus t minus 2 dx. And this integral right here will simply evaluate to 1 over n plus t minus 1. So finally, we can say that our f of t is equal to 1/2 the sum from n equals 0 to infinity of negative 1 to the n times n minus 1 over n plus t minus 1. All right, did I forget anything? 1/2, sum going from 0 to infinity, negative 1 to the n minus 1, and this evaluates to 1 over n plus t minus 1. So that's it. That's correct. So there's our f of t. All right. Well, now it's pretty easy to get our f prime of t, since the only thing in this sum that depends on t is the 1 over n plus t minus 1, which is just n plus t minus 1 to the negative 1. So that would just give us the negative of it squared. So our f prime of t is going to be equal to 1 half the sum as n goes from 0 to infinity of negative 1 to the n times n minus 1 all over negative, which we will bring outside, so that's going to be a negative 1 half, equals negative 1 half, and this will be n plus t minus 1 all squared. Okay. So I don't believe we need any of this stuff. We've obtained our f prime of t. Now all that's left to do is plug in these values. So we can erase all of this. Now it's just plugging numbers into an equation. Okay, but we have to do it carefully. So that means that I is going to be equal to this thing first is this thing evaluated at negative 1 half. So we're going to have negative 1 half the sum from n equals 0 to infinity of negative 1 to the n times n minus 1 all over n plus negative 1 half minus 1 is n minus 3 halves, n minus 3 halves squared. Did I do that part right? Yeah, we have the negative 1 half sum from n equals 0 to infinity. We got the negative 1 to the n, we got the n minus 1, and we simply replace this t with a negative 1 half. So that's negative 1 half minus 1 is negative 3 halves. So that's right. All right, and then we have minus f prime evaluated at 3 halves. Well, minus a minus is a plus. So now we have plus 1 half the sum from n equals 0 to infinity of negative 1 to the n times n minus 1 all over, let's see, this time it's going to be replaced with a 3 halves. So 3 halves minus 1 is 1 half. So that's n plus 1 half squared. N plus 1 half squared. All right, so what to do now? Well, what I'd like to do is kind of use a little trick on this part of the sum. Notice that we don't need the first two terms of this. The first term would evaluate to 0 due to this n, and the second term would evaluate to 0 due to this n minus 1. So we can actually start this at n equals 2. Right? Yeah. And now we can perform another trick where we subtract 2 from the index and add 2 to all of the n's inside the sum. So let's very carefully do that. Okay, we're subtracting 2 from the index. Now we'd get negative 1 to the n plus 2. It's equivalent to negative 1 to the n, so we'll leave that alone. This would become an n plus 2, and this would become an n plus 1. Okay, so I'm going to remember that and write that down. So we're going to have n plus 2 and n plus 1. Okay, adding 2 to this would give us n plus 1/2. Okay, now what do we do? I don't like this n plus 1/2 in the denominator, so what I'm going to do is multiply the top and the bottom by 4. So multiplying the top by 4 would just give us a negative 2 here. Multiplying the bottom by 4 would make this 2n plus 1. And we'll do the same thing on this side. So this is going to be 2, and this will become 2n plus 1. All right, now we're getting somewhere. So now what I'm gonna rewrite this thing below. Instead of rewriting it like this, I'm actually going to FOIL out this n plus 2 times n plus 1. And you know what? I'm just gonna, let's see, what would that be? That would be n squared plus, let's see, n plus 2n plus 3n plus 2, right? Yeah, n squared plus 3n plus 2. So I'll just go ahead and write that instead of this. So let's see, this is going to be n squared plus 3n plus 2. All right, and this would become n squared minus n. N squared minus n. All right. So now let's add these two sums together, and let's find out, let's see what we would get. All right. So we'd still have I is equal to, and then we definitely we'd have either a positive or negative 2. I'm not sure which one yet, but it's going to be a 2 somehow. So there's going to be a 2, and the sum is going to go from 0 to infinity, and we're still going to have this negative 1 to the n over 2n plus 1 all squared. And then we'd have, let's see, an n squared minus an n squared, so there's no n squareds. And then we'd have a negative n squared minus 3n squared. So that'd be a negative 4, I'm sorry, just n, negative 4n. And then we would have a negative n minus, wait a second. And then we'd simply have minus 2, right? Yeah. And then we'll factor out the negative sign to give us 4n plus 2. And then we'll factor out a 2, giving us 2n plus 1. And then we will cancel this with one of these, leaving us just negative 1 to the n over 2n plus 1. Well, great. We have it as a sum, but we can go further with this. We can go further with this sum right here. So let's recognize this, that the sum from n equals 0 to infinity of -1 to the n times x to the 2n is equal to 1 over x squared plus 1. Taking the antiderivative with respect to x on both sides would give us this, that the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1 is equal to arctangent x plus c. We'll take x to be 0, and we'll get 0 is equal to 0 plus c, making our c equal to 0. Okay, so now plugging in 1 for our x would give us this, that the sum from n equals 0 to infinity of -1 to the n over 2n plus 1 is equal to the arctangent of 1, which is equal to pi over 4. So this is equal to, what did I do wrong? I forgot that when I factored out a 2, so we should actually have this. It should actually be -4 times. Because remember earlier when I factored out that 2, I actually forgot to write that. So this is what it actually is. Let me go through that again just to be sure. All right, so on this we'd have a, let's see, we'd have an n squared minus n squared, so that's good. Then we'd have a -n minus a -n minus 3n. So it's minus 4n, and then we'd have a minus 2. So yeah, I just forgot to actually multiply this 2 by the 2 when I factored out the 2. Rewind the video and you'll see what I'm talking about, that this is actually what it is. Okay, so anyway, this is still true. So this right here is equal to pi over 4. So the entire thing is equal to -4 times pi over 4, or just negative pi. Okay, I think I won't redo this video. I think that's I'll leave that mistake in there, since I was able to catch it and explain it at the end. Like I said, rewind the video and you'll see what I was talking about. But anyway, there you go. That crazy integral right there evaluates to nothing but negative pi. So hope you enjoyed that.